Hi there, my name is Michael Landis. I'm an assistant professor at Washington University in St. Louis, and I'm here to share some of my recent work on modeling historical biogeography. And I'll be working within the GeoSSE framework. GeoSSE is a phylogenetic model of biogeography introduced by Emma Goldberg and others. And for those of you who aren't familiar with the GeoSSE model, for a quick review, GeoSSE essentially operates through four distinct mechanisms or sub-processes. First, we have dispersal. Species ranges can expand from one region into another through these dispersal events, modeled at rate r sub d. Species ranges can go extinct locally in certain regions through the extinction process r sub e. New lineages can arise through within-region speciation, r sub w, in one of any of the ancestral regions in a species range. And finally, between-region speciation acts upon widespread species and can split one lineage into two, presumably on the basis of the existence of like a geographical barrier severing gene flow between populations. Now, most biologists, if I gave them a simple geographical system such as this, where all regional features were identical to one another, they might think that the dispersal rates are probably equal to one another on the basis of geography alone, because distances are equal to one another. Extinction rates might be equal to one another because sizes are equal to one another, and so forth. Now, if regional features differed among regions, the same biologist might also assume that, let's say, dispersal rates would be greater between nearby regions, such as between A and B, compared to between different regions, such as A versus C. Extinction rates, speciation rates, and so forth might also vary in kind. And this is fairly easy to reason about with just three regions, but as the number of regions increases, the thinking becomes a little bit muddier for some, well, for me at least. And part of what becomes complicated about the problem is that as the number of regions increases on the left column there, up towards the number n, so the number of ranges explodes with the number 2 to the n. And many of the model parameters under a simple GeoSSE parameterization also increase, not just on the order of n, but say on the order of n squared for dispersal in blue, or on the order of e to the n for between region speciation events. And this is largely because there's so many distinct ways you can split a range, and there are quite a large number of ranges indeed. So for this short talk, I'm going to introduce I'm basically going to cover briefly two aspects of this study. First, a definition of a feature-informed GeoSSE model, and second, an application of that model to anoles biogeography. Now, for this feature-informed GeoSSE model, we have three layers for this model. First, the model has features that we can go and measure about geographical regions that exist in the real world, such as distances between regions, the presence or absence of categorically distinct types of barriers, the sizes of regions, and different categorical variables associated with the region, such as an island type. In between, and then at the bottom, we have the GeoSSE model, which accepts rates and converts those rates into likelihoods based on a biogeographical pattern and a phylogenetic pattern. In the middle, we're going to basically transform these features into model rates that GeoSSE can use. And I can't get into all the details for how this works, but I can give you a flavor for how it works just through a brief example focusing on extinction. And if you understand how extinction works superficially, you'll have some sense of how the other processes work as well. So here I have three regions, A, B, and C, with sizes 10, 2, and 5 respectively. And notice that only region B is an island. The other two are continental regions. Now, I could assign different values to different parameters in this model to emulate different biogeographical scenarios. Suppose extinction was equal everywhere. I could set a parameter in this model, the feature exponent, phi sub e, to be equal to 0. And what that would do is would cause all extinction rates to be equal in all regions according to the base rate, rho sub e. I could also say that I'd like my extinction rates to be faster in small regions. Well, if I set a negative value to e sub e, such as -1, I induce a negative relationship between region size and extinction rate. And now we see that region B has the highest extinction rate of 0.05. There's a categorical scalar which would say that regions of a certain type, say islands, would effectively have a different size compared to other counterparts like the continents. Here, the island size is effectively a tenth the size of a continent a continent of equivalent size too, and this causes the extinction rate for B to become even larger. And what's cool about this model is that with three parameters, I can now control variation with respect to these regional features for any number of regions, yet always using three parameters. And this would scale for any number of regions, 6 regions, 10 regions, 1,000 regions, and so forth. Now, the 4 subprocesses work similarly, but not identically. Between region speciation is the only one that operates in a fundamentally different way. And it has to do with the fact that we have so many distinct ways we can split ranges. And so the other models don't have that same problem. The other subprocesses don't have the same problem. To deal with this issue, we introduced a range split score called F sub B, and it's essentially a score for splitting a widespread species into 2 distinct subranges, S and T. And its interpretation is quite simple. If it's a high score, it's an easier split. And it's used to eventually compute event rates in the same way that we can compute event rates for extinction, as we saw before. Now, just to give you a flavor for how this works, the range split score is the inverse sum of inverse distances. And here I'm showing you a few of the computations for a 3-region system. We see that regions B and C are closest, regions A and B are second closest, and regions A and C are third closest. These measurements for distance would come from some type of parameterized geography, just like we use for extinction. And what we also see is that the range split scores are fairly sensible across different range splitting configurations. For example, splitting A and C has a higher score. It splits more easily than splitting B from C. And also splitting A from B and C, A being the most distant of any of the 3 regions from the other 2, has the highest score. So that's fairly reasonable, and it allows us to assign inequalities to different range split configurations. So now we have a feature-informed GeoSSE model for 12 parameters, 3 parameters per subprocess for any number of regions. I then took this framework and I plugged it into RevBayes, a Bayesian phylogenetics package that I helped develop. I introduced a few new GeoSSE functions to specify GeoSSE type models. For the SSE likelihoods, I'm using a new library developed by Mike May and Xavier Meyer, which is in preparation, called TensorPhylo. And for inference, I'm using MCMC to estimate parameters. And of course, as I said before, we're going to study Anolis biogeography. This is a first for me. It's kind of exciting. Many of you know Anolis lizards through their Caribbean distribution, but throughout the neotropics, they're much more widespread. And for the analysis, I'm using this POETL dataset from 2017. For it, I'm using 9 regions. 5 are encoded as continental, and 4 in the Caribbean are encoded as islands. When you look at where Anolis live today, it's quite interesting in its own right. 186 species are found only in 1 continental region. 164 are found only in 1 island region. And the remaining 29 species are all widespread in 2 or more regions, found only in adjacent continental regions, which is pretty fascinating when you think about how geography might be influencing that histogram. When you do a simple ancestral range estimate of the clade, you find there's 1 dispersal event from continental regions into island regions, 2 dispersal events from island regions into continental regions, and that's it. So continental and island affinities are highly conserved in this clade, and that's something that Steve Poe and others previously reported on. Now, to visualize rate variation across different region pairs, here I'm going to use a graphical representation. So here, nodes correspond to extinction rates, edges correspond to dispersal rates. If the feature has a heavy line, it's a high rate. If it's a thin line, it's a low rate. If it's purple, it's continental. If it's blue, it's related to an island. And what we find is that dispersal is most common between adjacent continental regions, and it's relatively rare when islands are involved. And extinction might be faster in larger regions. For within region speciation on nodes and between region speciation on edges, widespread continental ranges split slowly, but widespread ranges over water split rapidly. And region size doesn't seem to influence speciation rate. If we then took these dispersal rates and plotted them against our between region speciation rates on the x and y axes respectively, we find that any pair of regions that involves an island is above a intercept 0 slope 1 line where rates would be equal. What that says is that when islands are involved, they split faster than they disperse. When only continents are involved, you can get equal rates, and even rates for dispersal is faster than splitting. And we think this explains why only continental anoles are widespread. So to conclude, I introduced a model where regional features influence rates that also uses only 12 parameters for any number of regions. In terms of Anolis biogeography, distances in water seem to be very important, whereas sizes and insularity are not. Then finally, for future directions, all of the obvious candidates are on our minds, such as how do you incorporate multiple features, how do you compute split scores in a better way, how do you accommodate hidden states, incorporate paleo features, and integrate other traits with these types of models. So that's all I have to share. I'd like to thank my collaborators. I'd like to thank the TensorPhylo developers, the Anolis experts, and of course, several close colleagues for their ideas and feedback on the study. Thank you.